Hello students, welcome back to another video of electrostatics. So in the last video we have talked and learned about the Gauss's law. So in this particular video we'll be learning about the applications of Gauss's law, and to be very sure of, Gauss's law has a primary application to find out electric fields. Electric fields for those kind of things which are not uniform or which are not regular. For example, till now all the electric fields that we have been dealing with are for point charges, right? For any kind of point charge, we are able to write down the expression for electric field. But what about we give some charge to an irregular body? What about I give some charge to a strand of hair? Now, a particular hair is not a point charge, but if we charge a particular strand of hair, that hair can also lead us to an electric field. So how do you find out an expression for electric field for those kind of things? So in order to understand or in order to find out the expression for electric fields for any physical objects which are not point charges, in order to find electric fields for those kind of objects, we can use the Gauss's law. The help of Gauss's law actually eases out the problem to find out the electric field. So let us start by one of the very simplest form of finding out the electric field using Gauss's law. So we will be finding out electric field for a uniformly charged infinitely long line. You can take it as a strand of hair which is infinitely long, as I have given the example. So in order for this to be infinitely long, this particular strand of hair should extend up to infinity, and even here it should extend up to minus infinity. That is how we can understand that this particular strand or this particular line, it's just a one-dimensional thing. This is infinitely long. Now I have some amount of charge Q, suppose. This particular amount of charge is given to this line. Now what would happen if I give this particular amount of charge to this line? The whole strand of hair or the whole line is going to get equal amount of charge. That means what? The whole line is going to get uniformly charged. The amount of charge per unit length for the whole line would be same or would be uniform. So we represent that by lambda, which will then be known as charge density. Okay, so the charge density for this particular strand of hair or for this 1D line is represented by lambda, which is to be uniform. Now let us take the help of Gauss's law or the Gauss's theorem to find out the electric field for this particular strand of hair. If I assume Q to be of positive nature, the whole strand of hair is going to get a positive charge from plus infinity to minus infinity, right? Now what if I ask you to find out the electric field for this particular strand of hair at any particular point, let us say P. Let us take a point P, and if we need to find out the electric field at that particular point for this strand of hair, we cannot use the formula for point charge, because right now this charge is not behaving as a point charge, rather this charge is being submerged or being given all throughout uniformly along the length of the wire. So we need to get a different expression. So for that we'll be applying the Gauss's law. Let's see how. So in order to find out the electric field at the point P, the first thing that we need to draw is a Gaussian surface. Now what do you actually mean by a Gaussian surface? A Gaussian surface is nothing but an imaginary surface that helps out to draw a diagrammatic view including the object for which we need to find out the electric field. Now the definition might seem a bit weird, but I'm gonna draw a Gaussian surface and the things is going to be pretty simple after that. So before we start off, let us assume, since we are already asked to find out the electric field at the point P, will obviously be given the distance of the point from this particular line. By distance we mean the perpendicular distance. So let the distance of this particular point from this line be R. Okay, so we first need to draw the Gaussian surface, which will be the first step to find out the electric field. Now how do you draw a Gaussian surface for a single parameter object or a 1D object for which you need to find out the electric field? The Gaussian surface is primarily a cylinder. Now that cylinder should have an equal amount of radius. Okay, the radius of the cylinder should be equivalent to distance at which we are finding out the electric field. Now since we cannot draw an infinitely long cylinder, so we are going to keep out the length of the cylinder as L. Okay, so we'll be taking the length of the cylinder to be L, and the radius of the cylinder is to be taken as R itself, which is the same distance at which we are finding out the electric field. So let us close up the cylinder. Okay, so this particular cylinder that I have drawn will serve as the Gaussian surface for this particular strand of line which extends up to infinity. But the important point that is to be noted is we will not consider the length of the cylinder to be infinite as well. The length of the cylinder is considered over a finite length, that is L. So the finite length of the strand or the finite length of the line that we are considering is L for this case, and lambda is actually the charge density. Okay, now this particular strand of line was given a charge Q initially, as we've already discussed. So let us now try out to find out the electric field at point P. Now whenever we are talking about the cylinder, it consists of three surfaces, right? There will be two circular surfaces, the upper surface and the lower surface, and there will be one curved surface. Now if I need to draw the area vectors for the three surfaces, the area vectors for the upper circular surface would be in this particular direction. Let me take it as delta S1. These are the directions of the area vector. The direction for the lower circular surface, the direction of the area vector would be in the downward direction. That would be delta S2. And let the area vector for the curved surface be represented by delta S3. And obviously for the curved surface, if I am drawing out the the area vector along this surface, it would be directed in this particular direction. So let me take it as delta S3. Okay, now since we are giving positive charge to this particular line, so for a positive charge the electric field always extends radially outward. Hence if I need to draw the direction of the electric field at this particular point, the direction of the electric field is also going to be along the same direction as the area vector. So this is the direction of the electric field at this point. It is directed outward along the line joining the point and the strand of hair. Now if we see the direction of the electric field and the direction of the three area vectors, we see that this particular area vectors for the circular surfaces, they are making an angle of 90 degree with the electric field, whereas this particular area vector, which is for the curved surface area, that is making an angle of 0 degree with the electric field. Now by going from the formula of flux, electric flux, which is given by E dot delta S, which turns out to be E delta S cos of theta, if we apply this formula to find out electric flux, we can see that the theta for the first and the second area vector would be 90 degree. Hence the total flux for these two particular surfaces would be 0. But for the curved surface area, since the angle is 0 degree, for the curved surface area, since the angle is 0 degree between the area vector and the electric field, hence the only flux that we'll be getting would be for the curved surface area. Now taking that into consideration, we'll be applying the Gauss's formula. So now we'll be applying the Gauss's law for this particular surface, and hence we'll be finding out the total electric field at this point P, which is represented by E. So the Gauss's law says that the total flux phi total is always given by Q enclosed by epsilon naught. Now if we consider the cylinder to be a closed surface or to be a closed figure, so obviously the line falls exactly at the center of this particular cylinder, and hence all the charges that belongs to the length L would be inside the cylinder. So that charges which is enclosed by this particular length of line L, that would be the charge which is under this thing Q enclosed. Now phi total, in order to take the total phi, since we are having three surfaces, delta S1, delta S2 and delta S3, they are being together three phis, phi1 plus phi2 plus phi3, that should be equals to Q enclosed by epsilon naught. And as we have already discussed, the flux for the surface S1 and for the surface S2 would be 0, as the angle made by the electric field with these two surfaces is 90 degree and cos 90 degree turns out to be 0. So the only remaining flux that we'll be getting is for the surface S3. So I can write it as phi3 equals to Q by epsilon naught. Now phi can be written as E dot delta S3 equals to Q enclosed by epsilon naught. Now what would be the Q enclosed by this particular length of line? So we have already discussed the whole line is uniformly charged and the uniform charge density was represented by lambda, right? So in order to find out the charges for this particular length of line, if I take that as Q dash, that will be given by what? Lambda times of L, right? Charge density multiplied by the length over which we need the charge. If we multiply the charge density with that particular length, we'll be getting the charge which is enclosed by that particular surface. So this Q dash is nothing but the Q enclosed. So in place of Q enclosed, we can write it as lambda times of L by epsilon naught. Now E dot delta S3, I can write it as E delta S because cos 0 is 1. What would be the formula for area for a curved surface? That is given by 2 pi r into L, where r is the radius of the cylinder and L is the length of the cylinder. That will be equals to lambda into L by epsilon naught. So I can cancel out the L's on both the sides. So the final formula or the final expression of the electric field would come out to be lambda divided by 2 pi epsilon naught r. So this is the final expression for the electric field for a uniformly charged infinitely long line at a particular point P, which is lying at a distance r from the line. Okay, now if you check out the expression, or the important thing that we need to note is the length of the wire is not mandatorily required in the formula. There is no L represented in the formula, rather only the distance at which we need to find out the electric field is actually the main important parameter that we need to find out for getting the electric field. So that is all for the application of Gauss's law in a 1D dimensional line. Next up, in the next videos, we'll be talking about the other applications.